Chapter 12: Forces, Frictions, and Newton's Laws. 12.1 Forces. A powerful storm is approaching. The weather forecast calls for gale force winds. Many people in the city decide to leave work early in order to get home before things get worse. As shown in Figure 1, a man pushes ahead into a strong wind and shields himself from the driving rain with an umbrella. The strong wind makes it very difficult for him to hold onto his umbrella. To keep his umbrella from being pulled from his hands, he tightly squeezes the umbrella handle. Elsewhere, a store owner attempts to bring in a folding sign that hasn't blown away because it is chained to a pole. Wind is but one example of the many forces you experience every day. The study of forces is a very important part of physics. As you read this section, you will learn what forces are and how they will make things move. What is a force? The man out in the storm is battling the forces of wind. A force is a push or a pull that acts on an object. A force can cause a resting object to move, or it can accelerate a moving object by changing the object's speed or direction. The force is wind. Pushing against a man slows his speed. A strong gust could even change the direction in which he was moving. Measuring force. Forces are often easy to measure. In fact, if you've ever shopped at a grocery store, you may have measured forces using a spring scale like the one shown below in Figure 2. The stretch of the spring in the scale depends on the amount of weight, a type of force acting on it. As more fruit is placed on the scale, the spring is stretched farther and the scale reading increases. The units of force. Force is measured in newtons, abbreviated as N. 1 newton is the force that causes a 1 kilogram mass to accelerate at a rate of 1 meter per second each second. In fact, a newton is equal to 1 kilogram per meter per second squared. The name Newton, after Sir Isaac Newton, the English scientist who explained how force, mass, and acceleration are related. You'll learn more about the forces and mass in the next section. Representing force. You can use an arrow to represent the direction and strength of a force. The direction of the arrow represents the direction of the force. The length of the arrow represents the strength or magnitude of the force. These are also known as force diagrams. In Figure 2, the force arrow represents the weight of the items on the scale. Both arrows point down because weight always acts downward. The length of the arrows show you that the more weight acts on the scale in Figure 2b than 2a. Combining forces. Have you ever helped to push a car that has run out of gas? If you have, you were taking advantage of the fact that forces can be combined. The individual force of each person's push adds with the others into a large force that allows you to move the car. You can combine force arrows to show the result of how forces combine. That is, forces in the same direction add together, and forces in the opposite directions subtract from one another. The net force is the overall force acting on an object after the forces are combined. Balanced forces. Sometimes the net force acting on the object is zero. Look at the tug of war in Figure 3. Each group pulls on the rope with the same amount of force, but they pull in opposite directions. Neither group wins the tug of war because the forces of the rope are balanced. Balanced forces are forces that combine to produce a net force of zero. When the forces on an object are balanced, the net force is zero, and there is no change in the object's motion. Examples of balanced forces are common. For example, imagine two people locked in an arm wrestling match. Although neither person's arm may be moving, a pair of equal and opposite balanced forces are acting. An unlimited number of individual forces can act on an object and still produce a net force of zero. As shown in Figure 3, the individual force exerted by each person still results in a zero net force on the rope. Unbalanced forces. Often, The forces of an object are unbalanced. If you push hard against the side of a book that is resting on a table, the book will begin to move. This is an example of an unbalanced force. An unbalanced force is a force that results when the net force acting on an object is not equal to zero. When an unbalanced force acts on an object, the object accelerates or moves. Forces acting in opposite directions can also combine to produce an unbalanced force. When a team of people win a tug of war, they win by pulling with a greater force than the losing team. The two unequal forces act in opposite directions but combine to produce an unbalanced net force. The net force equals the size of the larger force minus the size of the smaller force. This unbalanced force causes the rope, the winning team, and the losing team to accelerate in the direction of the unbalanced force. Figure 4 shows several examples of how forces combine. Friction. All objects move or are subject to friction, a force that opposes the motion of objects that touch as they move past each other. Without friction, the world would be a very different place. In a frictionless world, every surface would be more slippery than a sheet of ice. Your food would slide off your fork. Walking would be impossible. Cars would slide around helplessly with their wheels spinning. Friction acts as the surface where objects are in contact. Note that in contact includes solid objects that are directly touching one another as well as objects moving through a liquid or gas. The four main types of friction are static, sliding, rolling, and fluid. Static friction. Imagine trying to pull a large potted tree across a patio. Although you apply force to the pot, by pushing it, you can't get the pot to move. As in figure 5 below, the force of static friction opposes your push. Static friction is the friction force that acts on the object that are not moving. Static friction always acts in the direction opposite to that of the applied force. You experience static friction every time you take a step. As you push off, with each step, static friction between the ground and your shoe keep your shoe from sliding. Sliding friction. With the help of a friend, you push on the pot with enough force to overcome the static friction. The pot slides across the patio as shown in figure 5b. Once the pot is moving, static friction no longer acts on it. Instead, a smaller friction force called sliding friction acts on the sliding pot. Sliding friction is a force that opposes the direction of the motion of an object as it slides over the surface. Because sliding friction is less than static friction, less force is needed to keep an object moving than to start it moving. Rolling friction. When an object rolls across a flat floor, both the object and the floor are bent slightly out of shape. This change in shape at the point of rolling contact is the cause of rolling friction, the friction force that acts on rolling objects. For a given set of materials, the force of a rolling friction is about 100 to 1,000 times less than the force of static or sliding. Because of this, professional movers often use wheeled dollies to move heavy objects. Ball bearings, like those shown in figure 6, are often used to reduce friction in machines. A ball bearing is made up of a set of round balls located between two smooth surfaces. The balls roll as the surfaces move past each other. Friction is greatly reduced between the surfaces because of the rolling friction replaces sliding friction. Inline skates, skateboards, bicycles, automobiles are just a few of the many machines that use ball bearings. Fluid friction. Friction also acts on a submarine moving through water and on an airplane flying through the air. Water is a mixture of gases such as air are known as fluids. The force of fluid friction opposes the motion of the object through a fluid. You feel fluid friction when stirring thick cake batter. The motion of a spoon through the batter is slowed by fluid friction. Fluid friction increases as the speed of the object moving through the fluid increases. Thus, the faster you stir, the greater the friction is. Fluid friction acting on an object moving through the air is known as air resistance. As higher speeds, At higher speeds, air resistance can become a significant force. For this reason, bicyclists and speed skaters often wear slick racing suits to reduce air resistance. Gravity. Why do leaves fall to the ground? The answer is gravity. Gravity is a force that acts between any two masses. Gravity is the attraction of force, that is, it pulls the objects together. The Earth's gravitational force exerts a force of attraction on every other object that is near Earth. That includes you. The force of Earth's gravity holds you to the ground. Note that the force of gravity does not require objects to be in contact for it to act on them. Unlike friction, gravity can act over large distances. Earth's gravity acts downward toward the center of the Earth. Fortunately, an upward force usually balances the downward force of gravity. What forces act on the boulder in Figure 7? Gravity pulls down on the boulder. An upward force supplied by the supporting rocks act upward and balances the downward gravitational force. Because the forces on the boulder are balanced, it remains at rest as it has for thousands of years. Falling objects. What forces affect the motion of a dollar bill dropped from the top of a tall building? Both gravity and air resistance affect the motion of the falling object. Gravity causes objects to accelerate downward, whereas air resistance acts in the direction opposite to the motion and reduces acceleration. In Figure 8, the flying squirrel has jumped from a tree and is falling toward the ground. As you can see, the squirrel has positioned its body parallel to the Earth's surface and spread its arms and legs. By doing this, the squirrel creates a very large surface. The large area maximizes the force of air resistance acting to slow the squirrel's downward acceleration. Because of the squirrel's slower downward acceleration, it is able to travel farther through the air than would otherwise be possible. As objects fall to the ground, they accelerate and gain speed. With increasing speed comes increasing air resistance. If the objects fall for a long time, the upward force of air resistance becomes equal to the downward force of gravity. At this time, the forces acting on the object are balanced. Acceleration is zero, and the object continues falling at a constant velocity. Terminal velocity is the constant velocity of a falling object when the force of air resistance equals the force of gravity. Projectile motion. When you throw a ball forward, you'll notice that it actually follows a curved path. The curved path is an example of projectile motion, the motion of a falling object. After it is given an initial forward velocity, air resistance and gravity are the only forces acting on the projectile. Figure 9 shows the motion of two balls released at the same time. Figure 9a shows the balls of different masses fall at the same rate. In Figure 9b, the curved path of the yellow ball is the result of the force of gravity and the initial horizontal velocity. The combination of an initial forward velocity and the downward vertical force of gravity causes the ball to follow a curved path. The two balls fall with the same acceleration and strike at the same time. Reviewing concepts. Question 1. How is the motion of an object affected when the force acts on it? Question 2. List the 4 types of friction. Question 3. How does air resistance affect the acceleration of a falling object? Question 4. Earth's gravitational force acts in what direction? And 5. Describe why a projectile follows a curved path. This concludes Chapter 12, Section 1.